Hello and welcome to this lesson on calculating surface areas. Oops, let me fix that. There we are. Alright, so calculating surface area. Suppose that S represents some surface defined by the function z is equal to f of xy above some region R in the xy plane. If f of x comma y and its partial derivatives exist on the closed region R, then the area of the surface S can be calculated by the following. So the surface area is equal to the iterated integral over that region R ds. Now this ds, when it converts into x's and y's, becomes this thing. So that's the iterated integral over that region of the square root of 1 plus f prime, no, not f prime, the derivative of f with respect to x squared plus the derivative of f with respect to y squared dA. So basically we're integrating over this region across that area. And this right here is sort of our formula that will help us calculate surface area once it's converted to x's and y's. Now, recall that if we wanted to calculate arc length, we ended up with a formula that looked like this. So if we have something that's a curve in the xy plane, not a three-dimensional shape, then the arc length is calculated by integrating along the x-axis, and we end up getting a formula like this. Well, our surface area is effectively a three-dimensional extension of arc length. And if you remember, we even saw an arc length formula for 3 dimensions, but that was just a single integral, meaning we were just integrating along some line. So now we're integrating across some area, and that gives us a surface area. Alright, so again, interpreting this formula, we're basically finding our surface area. So let's take a look at some examples. Alright, so example 1. Find the surface area of the part of the plane z is equal to 12 minus 2x minus 3y that lies above the xy plane in the first quadrant. So let's take a look at our solution. Using our formula for surface area S is equal to the iterated integral over our region of the square root of 1 plus the derivative of f with respect to x squared plus the derivative of f with respect to y squared, integrating across that area. So we get the double integral of the square root of 1 plus, well, the derivative with respect to x, that's a negative 2, so it's negative 2 squared. The derivative with respect to y, that's negative 3, so it's going to be a negative 3 squared. So 1 plus 4 plus 9, that ends up giving me a square root of 14. So now we have to interpret that region. So the xy trace of that plane looks something like this. So that plane comes through my xy, plane intersects my xy plane at this line, 2x plus 3y equal to 12. So plugging in 0 for z, that gives us where that plane intersects my xy plane. And the area that we want to find is above this shaded region. So we have to integrate over that shaded region. So describing that shaded region, that's going to give us y goes from 0 up to this line. And that line, when I solve it for y, is negative 2/3 x plus 4. And x is going to go from 0 out to 6. So updating my iterated integral, this gives me the following. The integral from 0 to 6, the integral from 0 to negative 2/3 x plus 4 times the square root of 14 dy dx. So starting to calculate that integral, pulling my square root of 14 out, integrating with respect to y, that gives me y evaluated from 0 to negative 2/3 x plus 4, which gives me a negative 2/3 x plus 4 dx. Integrating with respect to x, that ends up giving me a negative 1/3 x squared plus 4x going from 0 to 6. Plugging in my endpoints, that ends up giving me 12 times the square root of 14 after my arithmetic is done. So the surface area of the portion of the plane above the xy plane in the first quadrant is going to be 12 times the square root of 14. Let's take a look at another example. So here I'm using the same plane. So I want to find the surface area of the part of the plane z equals 12 minus 2x minus 3y that lies above a circle centered at the origin of radius 1 on the xy plane. So if you think about it, on the first example we had this diagonal plane and I was cutting a triangle out of it. Well, here I'm cutting a circle out of it. Well, it's a circle on the xy plane, but projecting it upwards, it's going to create something more like an oval. So our solution, we're going to use our surface area integral. So plugging in our derivative with respect to x, our derivative with respect to y. This ends up giving us the integral over that region of the square root of 14 dA. And then I'm going to take out that square root of 14 and basically get the square root of 14 times the iterated integral across that region of that area. Now the last time I did this, I set this up as a double integral, finding the areas, the endpoints of those areas, but effectively with that first one what I was doing was I was finding the area of this particular triangle. Well, we have a formula for the area of a triangle, and that's 1/2 the height times the base. So 1/2 the height, which would be 1/2, 4 is 2, and then 2 times 6, that's 12. That ended up giving my 12 times the square root of 14. Well, if I'd noticed that at the beginning, that all this is doing here is calculating the area of that region, then I can just sit there and use my formula for the area of a circle, which is 2 pi times the radius. So that gives me 2 pi times 1. And then times the square root of 14 out there, that gives me 2 pi times the square root of 14. Now the reason why these two work so nicely like that, is because when we calculated that square root, we ended up with a nice number inside the square root, a nice constant. Sometimes inside that square root we're going to have some variables. And if you have some variables inside your integral, then you're going to have to integrate it like you normally would, like the first one that I did. But if all you have is just a constant inside that integral, then you can just pull that constant out and then just calculate the area using your regular area formulas. Alright, so let's take a look at a variation of this, something called surface integrals. So, we've taken a look at how to find the area of a surface in three-dimensional space. So let's say that S represents some surface in three-dimensional space defined by the function z is equal to f of x comma y. And that surface is above some region R in the xy plane. And let's suppose that function g of x comma y comma z is a function that represents some property in three-dimensional space that contains our surface. So an example of this property might be density. So if its density and we have a surface that is not flat, and we're integrating density over that surface, then what we have done is we found the mass of that shape, that surface. So, assuming that the first partial derivatives of f of x comma y exist on that closed region R, then what we can do is we can set up something called a surface integral, where basically we're integrating our function over that surface. That's what that ds represents. We're integrating over the surface. dA means we're integrating over some area, sort of in the xy plane. ds means we're integrating over some surface. So the integral over a surface of this function, well, this ds becomes this square root of 1 plus the partial derivative with respect to f squared plus the partial derivative with respect to y squared dA, where now we're integrating with respect to x and y. So what this is going to do, this integrates, it adds up all the values of g over that surface. Now, since we have not seen integration in 3 variables yet, what we are going to do is we are going to replace z with f of x comma y. So updating our formulas gives us that our surface integral is going to be the iterated integral over that region in the xy plane of g of xy, and then instead of z here, I'm going to have that function for z, whatever that is, and then ds, which again is effectively the same thing when you rewrite it with the dA notation. Alright, so thank you for watching this lesson on surface integrals and calculating surface areas, and I hope to see you next time.